absorbing system.
Yes.
Except the slides on the left.
Say again?
Except the slides on the left.
Hit F5.
Very good.
Hello, I'm Harold Hastings. This is my teammate Alexander Zuleta. We are T12-Vibranium, and we're going to be presenting our shape memory alloy passive shock absorber.
The purpose of this prototype is to create a variable absorber which can change the damping ratio by changing the temperature. What we want is to change the characteristics of the system and effectively attenuate high amplitude vibrations. What we want to approach is 1 degree of freedom system, which will consist of 1 spring, the damper, and 1 mass. So we're going to build a prototype that uses this type of analysis. We're going to create a transfer function, which is going to get the output and the input. We're going to make a ratio, and then we're going to compare through different frequencies to see how effectively we can shift or move the natural frequency of the system and create a variable damping system. To analyze the system, we need to get the material right. So what we did is we found that resilience is a property that describes how a material can behave as a spring. If the resilience is high, it means that the material can behave as a spring. So we made a table with very common steels that are used in suspensions, and then we calculate the resilience for the nitinol, which is our material. We found out that it's very close and it's also high, so right now we could proceed for the analysis. We found these formulas which relate the K factor of the spring in terms of the shear stress, the diameter of the wire, and also the diameter of the spring. So doing that and taking G as a function of temperature, because the material changes stiffness, the Young's modulus changes as you change the temperature. So we put this function inside this other function, and then we start to tabulate, as we see, to find the optimal wire diameter that will give us the K factor as we want for a scale model. This is a digital prototype. What we implemented is 4 springs at the top, 4 springs at the bottom, made out of nitinol. We're going to connect a system which will control the temperature by injecting electricity through the wire. Since it has resistivity, it will produce heat. The phase will go from martensite to austenite. It will become very soft to a very stiff, and after cooling, it will go back to martensite. Through that phase transformation, it will absorb energy, it will create latent heat, and will dissipate the energy of the vibration.
Actually, I want to add something. One of our design goals was to make a shock absorber that would retrofit, if you will, the current shock absorbing systems. So you should notice that the main housing is the same shape and style as the tubes that are in use now, and we have guide rods that we implemented here. We have guide rods that we implemented here to prevent buckling, and we also have a plate right here, which is basically the mounting point for the springs for the top and bottom. And the bottom tube moves relative to the top tube, so everything moves in tandem. So I want to add that. As far as simulations are concerned, we found the nitinol model on SolidWorks. We're still trying to get all the proper material characteristics in order for it to function properly, as nitinol is not a linear acting material. It's non-linear. And we did stress analysis based on nitinol material as a spring in the 2 different modes. And we also did a quick fatigue study. Now we know that this fatigue study is based on, I believe the steel curve is what we used. So it's not completely accurate, but we will find a way to intercept that. But this is just, you know, intermediate results right now. As far as the prototyping is concerned, we are going to use the nitinol we're going to buy in wire form, and we're going to create jigs and fixtures in order to create them ourselves. We will mold them and then anneal them at approximately 500 degrees Celsius. We will use nonlinear nitinol models for simulations, and we will also look into developing a thermal delivery system which will control the phase temperature. This is our timeline as of right now. Okay. Oops. Possible outcomes are expected, unexpected. Next. And our global considerations will include calculations in both English and SI units, an instruction manual in multiple languages, and as far as the global impact, this would provide a system that would need low maintenance and have long-lasting capabilities in areas that do not have the same resources as first world countries, for instance. Next. Material sources, we are going to look into local sources. We have listed 2 here, memory and nitinol.com. Next. We also have overseas sources, and we also have basic outline of what nitinol is. It's a binary alloy made of nickel and titanium, and we have some of the possible repercussions of mining that, because it is kind of dirty to mine nickel. There's a lot of environmental considerations. Next. And that's it. Okay.
Right there on your cover page, you might want to either use a different color fonts or larger fonts,
Okay.
so we can see your names from back here. I can't see it, even with my binoculars on right now.
Okay.
All right. I don't have any criticism or other comments.
Okay. Thank you.
Which program did you use for your analysis?
SolidWorks. We are looking into ANSYS, but in order to do the nonlinear analysis with SolidWorks, with ANSYS and nitinol, we have to basically create a subroutine in order for it to work properly, or we can buy from the company, which is several $1,000s, neither of which we can do right now. So we're looking into other means, but we are hoping to use ANSYS for the majority of our analysis.
What's the budget?
Budget right now is,
Did you have a slide on that?
no,
Okay.
we didn't.
Okay.
The material is becoming popular. It's lowering. The price is low right now since it's being used in the medicine industry. So it's around, like, for 1 foot, it's around $20 per foot, but it increases as you increase the diameter. So that's spending, because we don't know yet what is the diameter of the design, because we're still making the calculations on the tables.
But for cursory estimates, we're guessing right around $1,200 for the tooling, the machine, the fixtures, and the raw materials.
Well, to the extent that you can, it may be a good idea to have a slide dealing with the budget,
Okay.
even if it's qualitative and not quantitative.
Okay. Okay, so we'll definitely
Okay, can you go back to your second slide? There was a picture and it was not good. Could you please find another picture instead of that one?
first slide.
Mass.
Okay. Because
Yeah, this picture.
it's not legible, right?
It's
You
not
can't read it? Okay.
very good. I mean, you can
Yeah,
find
or
it.
touch it up.
Okay.
Yeah, or you can take it into a program and touch it up and,
Yeah.
and make it clearer.
Okay. Done.
And you spent 6 minutes, 45 seconds for your presentation now. 6:45.
Okay.
You should
Next
some
time,
off.
try to be on time.
They need to shave some time off.
Yeah.
Yeah.
You could probably,
We were under the
Be
impression
less
it's supposed to be
verbose
a
if-
10-minute.
No.
no,
5 minutes
5
for
minutes.
5 and
introduction.
10.
5 minutes for presentation, 10 minutes for questions.
Yeah.
that's it.
Oh, I had
You had it the other way around.
Okay.
No.
Okay, so we can.
Well, what you can do is you can condense some of what you said into a graphic. You can do that, get creative with that. You know what I'm saying?
Yes, I do. Okay. So more visualizations, less on the
Mhm.
verbosity.
And you can add cost analysis slide if you want, right?
Mhm.
Okay.
Timeline. Can you see your timeline? Ah, good.
Yeah, timeline was good.
Timeline was.
Yeah.
Yeah. All right.
Any questions, suggestions?
No, they're good,
Okay.
except for the time-wise.